Hi, my name is Farhan Mansoor, and this is my final project on text summarization. Um, so in this project, basically what I did is I explored various approaches to summarization problem, and then I used news articles as my context. So what I will do is I will explore extractive summarization using rule-based algorithm as well as abstractive summarization using deep learning models, and then we'll assess the effectiveness of each approach. We'll evaluate them using Rouge scores, which is like a popular metric that measures how well the generated summaries align with reference summaries. Most of the modules are basically TensorFlow framework, and there are a couple stuff that I'm using from sklearn and transformers module from Hugging Face for fine tuning that we'll see at the end. Um, so let's talk about the data set a little bit. So the data set is basically a curated set of news articles collected from CNN, Daily Mail data, and you can find the data set in many places like Kaggle or Hugging Face. Here, what I'm doing is I'm just using Hugging Face's module, load dataset module to directly download the data, but you can also manually download it from either Kaggle or Hugging Face. So initially, what I'm doing here is I'm splitting the data into a training, validation, and test data frame. And here is this kind of a quick overview of what's in those data set. So basically, it has three columns: one for the actual articles, the large articles, and then there's a column for the highlights or the summaries of each article. Um, and in total, there are about like 300,000, or a little bit, or slightly over 300,000 pairs of articles and highlights. They're split into about 287,000 training pairs, and then we have about 11,490 pairs of test. And validation is, so I don't know what I had there. So okay, so the validation version set is about 13,000. 13,000 rows. So that's kind of the split that this data set has. Um, Next, let's try to visualize the data a little bit just to see. So the only thing that was kind of important for training purpose later on we'll see is the kind of the word count distribution. So I wanted to see how many words were in each of these articles, because the longer the text is, it's harder to train on them. It takes longer time. So if we look at the data for the for the articles that are in the training data set, you will see that this is kind of the distribution of word count. So most of them are between 150 words to, let's say, 1250 words, and there are some longer articles that are like closer to 2000 words, but most of them are between 150 and 1250, with an average of 692 words. And if we look at the summary distribution, so the summary or the highlights are basically, this is what the distribution look like. There are some outliers where it has very high word count, but in most cases it's between 10 and 130 words with an average of 52 words. So then what I did initially to get started is start processing the data. So I started taking a subset. So the reason I took a subset because I wanted to exclude some of those longer articles. So this is kind of the restriction I put together to make sure I don't lose too much data, but then also avoid training on very large articles. Um, so I used a minimum length of 200 and a maximum length of 1100 for the articles, and similarly for the highlights or summaries, I used 20 to 120 words. Um, and I took a subset based on those requirements, and this is what the kind of the final split of data looks like based on that requirement. Then what I did is I cleaned the data. Nothing too complicated. Basically, taking out some white spaces, converting to lower cases, taking out some uh, irrelevant tags. For example, some of the articles had this editor's note or new, kind of those keywords at the beginning that I took out to make it more clean. So this is what it looks like after applying the clean function. So you can see everything is in lowercase and doesn't have special white space or characters at the beginning. Then the next step was to build a tokenizer. So what I am doing here is I'm using this framework called Sentence Piece, which basically is a custom tokenizer that you can build on your text. And the advantage of using this is it creates a vocabulary at a sub token level, meaning it will split words into subwords, and then this allows us to train faster. We'll see at the end. Um, uh, so it's kind of like creating subtokens. In order to build something like this, what I did here is I'm using the sentence piece framework, and then initially, in order to train this tokenizer, I had to create this text file with all the text I have for training. So in this case, I used the training and the validation data together. I kept the test data separate because we don't want to include that into any sort of modeling. So I used the training articles and training highlights as well as validation article and validation highlights to kind of create this corpus file, right? So that has all these text in text format. And then I just saved it locally, and I passed it to the trainer for the tokenizer trainer function with a fixed size of vocabulary. Now I used the 10,000 vocabulary size because that kind of was optimal. Like after a few trial and error, it's not too big for training and it's not too small so that it doesn't lose information. So using this, what happens is it takes like a few minutes to train, and then it creates this tokenizer model that can now be used to tokenize your text, input to output text from this point. So I use this tokenizer to so you can see this is kind of, I'm testing the tokenizer here. It shows you the first 20 tokens. So you can see this automatically adds this start and end token that we'll be using later on for training. And then there are some tokens here as well. You can see sometimes it breaks words into multiple phrases. So th, that, there are a few that where you will break it into subwords. But the lookup size, it keeps that at 10,000 because that's what I specified. So now after we build the tokenizer, I'm going to start with our kind of experiments and approaches. So the first thing I explored is using extractive summarization using TF-IDF. So this is not a deep learning model. We're not training anything yet. It's just going to use this rule-based algorithm to kind of select the most important sentences from an article, and then we'll put together those important sentences as a summary. So in order to do that, what the algorithm that I'm using here is the TF-IDF score. So basically, just to give you an overview of what that is, the TF is basically the term frequency, and it measures how frequently a term appear in a document, and it will give higher weight to words that appear more frequently in the sentence. The inverse document frequency is basically, it measures how unique or rare a term is across documents. In this case, our article. So basically, what it does, it will penalize common words, right, and then it will emphasize on rare, more informative words to represent more meaning from the articles. And together, these two kind of what makes the TF-IDF score, and that's kind of the formula here. So what I did here is I used this TF-IDF vectorizer, so from sklearn, and what it does, if you give it a sentence, it will basically find each word's TF-IDF score, and it will generate a matrix. So what it's doing is here I'm basically using this TF-IDF vectorizer here and applying it on my sentences from the article. So now what I'm doing here just before this step is I'm actually generating the sentences from the articles, which is like taking the article and then splitting into individual sentences using this send tokenize function from the NLTK module. Uh, Essentially, what it does, it will take the article and then it will just break it into, by punctuation or by meaningful pieces, and then each piece will get fed to this vectorizer to create the TF-IDF score. And based on the score, we will have a rank of the sentences. And here I'm choosing the top two sentences, but you can choose 3 or 4 sentences depending on the use case. So here I'm choosing the top two sentences to create a summary, and this is an example summary it puts together. So what it basically doing is just ranking the sentences and then chose 2 best sentence that it thinks has the highest score, and then it will put it together. Now it works kind of, so the summary makes sense. I mean, it's not anything fancy. It's just picking sentences that it thinks has the most relevance to the article, and then putting together a, a, a summary. So this is basically an extractive summary where it's not paraphrasing anything or it's not understanding the context. It's just putting together meaningful sentences together. Um, in order to evaluate how good these summaries are, so this is the Rouge function that I'm using. So this is basically a popular metric that people use to compare generative summary with a reference summary. And the way it works is the Rouge one, the metric is basically measures one word overlap. So how the individual words, how good they are with the reference summary. And the Rouge 2 score is basically 2 words or bigram overlaps. And then there's also Rouge L, which kind of deals with longer sequence of words and how they appear in both reference and your generative summary. So the ideal rule of thumb is about 0.4 is a good score for Rouge 1. Well, more than 0.3. Anything more than 0.3 to 4 is a good score. Rouge 1 is more than 0.2 is a good score, and Rouge L would be around 0.3. So based on the reference score, this is doing reasonably okay. I mean, it's not super high, but it's reasonable. Now, in the next experiment, what I tried is actually tried to do abstractive summarization model using transformers. So again, to start with, I had to tokenize the data. So I'm using this tokenize function, right? And then it's using our pre-built tokenizer from sentence piece, right, that we made, and it will basically take our training data set and will convert into input tokens and target tokens that will then get fed to a transformer model for training. I'm using the same functions that we used in class to build a model. I could not try any complicated layers because I'm only using one encoder and decoder layer to train this model. And I'm using 128 as my embed dimension and then 512 as my latent dimension. I could not try anything more because of resource limitation. This model has about 6 million parameters, and I kind of trained it in 3 steps where I trained for 10 epochs first, and then 5, and then 10 again. At the end, this is what the training and validation loss and accuracy looks like. And here's kind of a sample summary. So I created this function to generate the summaries by taking the prediction for the model and then decoding it via the tokenizer. And at the end, this is kind of the summary we're putting together now. You can see it. This is the article about the dog that was injured and then was treated in the hospital. So it was able to create sentences and put together, but it's not very useful. It's not very meaningful. So it is. I mean, it requires improvements. That's the bottom line. It requires more complexity and probably bigger data set. And here's for training. And here is the Rouge score for the models. For the model, as it can be seen, the model is not very accurate based on the score. Scores are low over all the metrics. The third experiment that I tried is fine-tuning a pre-trained model. So in this case, I used a BART model. So initially what I did is I downloaded the model and then I prepared it for fine-tuning. So instead of feeding all the data, I only fed about 10,000 samples just to demonstrate that it's much easier to train a pre-trained model with very small data set. And even with the 10,000 samples, it was able to train to a very good score. So I I actually trained only for 10 epochs, and here is the summary. Here are some of the summaries that it was generating, and you can see the summaries are pretty good, standard charter signed up, and it makes kind of sense when you read through it. Um, Here I'm using a kind of a loop to generate all the summaries using the model's prediction. The Rouge scores are pretty good. If you look at it, this is like 0.3 and 0.2 for the Rouge 2, which is on par. And the fact that we only trained for with only 10,000 samples, it means that we can improve it even further by feeding more training data and training for longer period of time. And so this approach looks like the more practical, approach. If we could use a pre-trained model, it already knows a lot of the language patterns, and then you can just fine-tune with your custom data set. Just to compare those three approaches, this is kind of a plot that shows all the Rouge scores of all the three approaches. As you can clearly see, the abstractive summarization by fine-tuning performs the best, even though it was only trained with a very small data set. The extractive summarization does well on paper, but when you read the summaries, it looks very. It doesn't look smart. I mean, it is just taking sentences from the original articles. The transformer model from scratch that I tried to train, it does okay with the Rouge 1 score, but it's not that good. I think it needs more improvement, and some of the improvements that we could make is adding more complexity to the structure, adding more encoding decoding layer, and feeding more data, training for a longer period of time. That might improve it more, but still the more practical approach would be taking a pre-trained model and then fine-tuning with your custom data set. I think that has the most real-world applications.